expressing this to you.
Grace, where are you?
It's so quiet without you.
No one's being mean to me.
I feel.
Don't be bullied, surfers.
Okay,
Yes.
so this is the part that's a really good, I'm sorry, it's small, I'll read it off. It's a really good explanation. For anytime you have to justify your statement or explain what this means. The greater the E cell, the greater the driving force, which is that whole EMF thing, electromotive force again. So they're directly related. So the greater the driving force of the electrons through the system, which means that the reaction will be more likely to proceed. It's more spontaneous. So if you have an E cell of one reaction, that might be, 0.70 volts, and you have another E cell that's 2.7 volts, then you're going to say the larger E cell means it's a larger driving force, which means it's more spontaneous than the other. So these are all directly related. E cell gives free energy, electromotive force, spontaneity in the forward direction, or thermodynamically favorable in the forward direction. So they're all talking about going forward, because we've set it up that way. Eventually, we will talk about equilibrium with this. If you get to the point where, this is just a fun fact, I don't know if I actually mentioned this last week. If you get to the point where you have an E cell of 0, that means your battery's dead. Okay? There's no driving force of electrons. Electrons are not being transferred. Nothing is actually conducting electricity. So it means your battery is dead. And I think that makes sense if you know what E cell means. It means the ability of the electron to be forced to the next place. So I think that makes sense, actually. But we've all experienced an E naught cell of 0, unfortunately. That sad day when your cell phone dies during class and you're like, I can't text anybody. Yeah.
Do battery testers test the E cells?
You mean like the ones where you push on it, it tells like the length of the battery life?
Like the ones where you just put it in the, it's like a battery socket, so it shows a light if it's red or green.
I'm thinking of the ones where you push on the battery to look and see how much longer, how much juice you got left in it. That's a different type of cell. That's actually 6 to 8 cells, like these kinds of cells inside. They're like little tiny cylinders, but that's testing lithium-ion batteries or nickel something batteries. It's a little bit different. They can test the length of time that's left of it. I don't think it tests the voltage, because the voltage is supposed to be consistent as long as you've got the cells there. So it's like it's a 1.5 volt or 9 volt or 12.5 volt. I don't know what all the voltages are of batteries. That's the extent knowledge I have. Okay, and then this is going to be telling us more about volts. We previously talked about what volts were, from what amps were, but you're going to be using a voltmeter today. Just write down the black part up here. We'll do this part tomorrow. Yeah. So a volt is going to be 1 joule. So 1 volt is 1 joule per coulomb. Coulomb, they're real cool. The coulomb is a unit of charge for electrochemistry. It is an SI unit. My kids are right now at honors camera like, what's a coulomb? Like, don't worry about it. You're never going to use it until spring semester baby chemistry, okay? It's a charge referred to from a bunch of electrons. It's just an associated unit. So that's what a joule is. All right, let's check batteries. Your batteries, were they fun?
Yeah.
Look, I thoroughly enjoy drawing some batteries.
Oh, we know.
Yeah. That's just a dash. Sorry, that's just a dash. All right, I'm gonna go over all of them really quickly, and then I know I've got to talk about the last two. Forgive my drawings; they were scanned and they look a little ratchet, but they're up here. Okay. So you have the chromium 3+ antidichromate, and then the chlorine gas 2 chloride. Noticing in the reactants here, do we have any solids? Nay. Okay, no solids, which means that you have to use platinum when you're drawing your cells. Your balanced chemical equation: 7 waters plus 2 chromium 3+ plus 3 chlorine gases yields dichromate plus 14 H+ plus 6 chlorides. You should have been able to figure out who was oil and who was rig based on the fact that you had to make the cell a positive E cell, so you could kind of finagle, looking at your like little mini sheet you had, that since E cell has to be positive, you should have been able to tell me who was going to be oxidized, who was reduced, because there's only one way to subtract them to make a positive number. So the chlorine is rigged, so it's got to be in the cathode. The chromium 3+ is oiled, so it's got to be in the anode. Good so far? Okay. So when you're drawing it, You can see I have a platinum electrode and a platinum electrode. Chromium 3 plus, I went ahead and put all the ions in here to show these are all the reactants, but it would have been okay if you just put chromium 3 plus and the dichromate, because they're the two things that make you have to start with the chromium 3 plus to make the dichromate. I didn't go through an example like this last week, so I'm glad that we're doing this one. Yeah.
With the metals that you insert, can you do like one platinum and one graphite? Or...
Yeah.
Oh.
Yeah, you can do whatever you want, as long as they're not reacting like this. So that's why I say only graphite and platinum. So I put all the reactants here that are associated with the half reaction of the anode, and then all the reactants are anode products here that are associated with the reaction of the cathode, which is chlorine gas is making chlorides. And I'm not asking for like stoichiometric numbers, like, you know, twice as many of these or 3 times as many of these. I just want them listed, that's it. So this truly you could have drawn as bubbles if you wanted to. And one of the reactions we'll see on Friday, we'll see bubbles, and you will actually draw those bubbles associated with the reactions. So the voltage should have been 0.03 volts, so really, really weak battery, like almost nothing. And then your cell diagram, cell notation diagram, line diagram, was the solid electrodes of platinum, the ions in reaction, and this one, it's the reactant and product, the half reaction. Double line meaning salt bridge, and then the reactant and product in the rig, half reaction, and then finally your electrode. It's just showing, because you have to show both of them, because you have to know who is made whenever you release electrons or take electrons. Normally we wouldn't see this many ions in here or gases in here, because normally what's being made is solid, you know, copper or zinc 2 plus ion. So normally the electrode is involved, so you don't see as many in these, okay? How are these, okay? Yeah? Okay. So I just said metallic, make sure no ions or gases, because you can't have a solid dose. This one I think was easy. 2.71 volts. Check yourself. You wreck yourself. Okay. So this one is, I don't think I need to go over in depth, because it's like the ones we did in class, metal, ion, metal, ion. Who would be forming a beard? Right, you could have drawn a beard here, and a little V here to show it's disappearing. If you want to get real information filled here. And then the salt bridge, that as this loses electrons, it's becoming more positive, so the anion is attracted. In this case, what's the anion in my salt bridge? What was the general one I said to use? Potassium nitrate. So nitrate would be traveling that way, and then this one is getting more negative as it gains electrons generally in the cathode. So as it gets more negative, the electron or the charge balance that has to occur as cation travels this way. So potassium would be traveling. This was a question on the AP exam last year. It said, here is a cell, an electrochemical cell, spontaneous. It gave you a little bit more. It gave you different reactants, but it said, draw what's in the salt bridge. And it said, draw it, you know, in the appropriate areas that correlate with the anode reaction and the cathode reaction. So you literally had to put NO3 travels that way, and then K plus travels that way. And some people were like, I've never had to draw that before, so I like drawing these. And sometimes I'll say draw the specific ions, but most of the time we just put the charges. Okay, you're still here. Okay. This one had, oh yeah, this one had gases in it. Okay, so we had the chlorine gas diatomic and the bromine gas diatomic. Bromine gas is actually not diatomic. Bromine diatomic is not actually gas at room temperature. It's liquid. Remember that? Random fact, right? So either way, you'll get credit. Don't worry about that. But I didn't actually list the states. When you look at the half reactions and the reduction potential, the bromine had a lower reduction potential. The chlorine had a higher reduction potential. So this is the one that is Rig, and I have it right here. Chlorine 2 plus 2 electrons yields chloride, or 2 chlorides, and then 2 bromides yields bromine plus 2 electrons. So they were fine in terms of electron balance. Balance it out. You get a 0.29 voltage whenever you take your red minus ox. And yeah, I don't know why that looks weird. So then in my drawings, I had platinum and platinum because I had no solids whatsoever. So I put both my ion and my product here, and then my reactant, which was chlorine, in my product here, because they both have to be represented to show the whole half reaction that's going on. And when you draw out your line diagram, platinum, 2 bromide things, double line salt bridge, 2 chloride things, and then platinum. Or graphite, whatever you want to do. last one, you were given the reduction potential for the iodate and iodide, or per iodate and per iodate and iodate. And so you were given, let's see here. I don't have my, oh yes I do, down here. Let me scroll back up in a second. This one was 1.539, so it's more positive, so that's the one that's being reduced. And then the permanganese one was the lower of the reduction potential, so that's the one being oxidized. So you do 1.593 minus 1.51. So then you got a really, really small voltage, 0.029. This one you'll notice, do we have any solids? Nah, we got all ions here. So we had to go through, yet again, platinum and platinum on both of them. And your platinum and then manganese and permanganate. Was the manganese, was reacting? Yeah. Was a reactant. Permanganate was the product, and then iodate and iodate and periodate were the reactants and products. And then you have your salt bridge in here. So I normally will always put my anode on the left and my cathode on the right, but be careful, sometimes it won't be that way, like on pre-designed images or diagrams for you, okay? Alright, do I need to cover anything else here? Okay, so we'll do the lab, pull out your lab stuff. I just want to give you 2 tips because you're going to have to get the voltages to make a galvanic cell. What sign would you want associated with your voltage? Positive. So I just want you to be careful with the 2 leads. I don't know if you've ever used alligator clips before. I have 2 colors, a red lead and a black lead, and they have alligator clips on the ends. You don't actually have to clip them to anything, you can just touch them, because it's just the touching of the to the electrode that will create the battery. You don't have to clip them, that's okay. So just make sure that whenever you're noting on the data tables, which is the cathode, which is the anode, the cathode we're going to call the positive, and the anode we're going to call the negative, and that's not always what you would call them on like a battery. It's in this lab right here, we're looking as if we are the voltmeter. If we are the voltmeter, then we're reading the anode as the negative, because if I'm the voltmeter, I can see the electrons coming to me from the anode. So what does it look like the anode is? It's negative. It looks like it's giving me negatives. I see the negatives coming towards me. And I can see the negatives going towards the cathode, so it looks as if the cathode is positive because it's attracting those electrons. So that's just in reference to the voltmeter. And then must have a positive E cell, so make sure that when you're doing it, if you end up with a negative voltage, you need to flip your wires because you don't have the correct cathode and anode notated from the voltmeter's perspective. So we want a positive one because we want it to be galvanic, spontaneous. So please record, so if your red one is on the metal 1 and your anode or your black one is on metal 3, you need to note that down because you're going to forget by the time you're doing anything else. It's like, oh crap, which was the anode, which was cathode, based on how you wrote it. So just make sure you record everything as you go. Take pictures of it, I don't really care. So a positive reading means the red is the higher potential. What am I telling you in chemistry code right here? The red one is the higher, right, that's the higher potential, means that's the rig, which means it's the what? Cathode, all right. So if you have a positive reading, it means the red lead is the rig reaction, which is the cathode, and then vice versa for the black wire. The very beginning of the lab, I think it says like touch your 2 wires together to zero out the voltage. Just you will have to touch them together. You're not going to shock yourself, okay? You're just going to have to touch them together. Don't freak out. Like, I'm not going to touch them together. Oh my gosh, when we were doing the electrochemistry stuff with the elementary schoolers, not electrochemistry, conductive stuff, they thought everything was going to shock them. I'm not touching it. It's funny. Okay, so we have metals 1 through 5. They're unknowns. Think about what metals I have access to, and I did have to make one of the metals. It's not ideal. It's kind of crusty and powdery versus like a solid. So just deal with me on that one. Your metal samples, most of them are great, but one of them is like kind of like, so just work with me. I'll tell you why later. Everything is in dropper bottles. Be controlled with your drops, so you're not going to have the same results as somebody else. And we will compare at the end to see who got like the best results. Oh, and step 5, you're gonna have to, you probably saw in the diagrams, you're gonna have to like cut out this little star looking thing, and you're gonna put metals here, and you're gonna, to make your cells, you need to connect this metal to this metal with a salt bridge. You're gonna have to make a nice droppage of sodium nitrate, which is what it says it on the model, and you're gonna touch your 2 leads here, and then you're gonna make a salt bridge here, and you connect these 2, and you're gonna do these. So you just need to make sure your salt bridges are nice and moist. Moist is a great word. Nice and connected, so that you don't have any gaps in your voltage. This says optional part. It's not optional. You're doing it. And the values that you have, I will have this up here for you. This is the complete list from your book, but you also have access to your own reduction charts, okay? So if you can't find something, you're like, oh, I want a more complete list, this one's pretty complete too. So just measure them. Your values are going to be perfect. Just kind of guesstimate where you think you're moving, okay? I'll show you where everything is. You're mixing up your groups. Make 5 new groups, get the computers pulled up, and then I'll tell you what I want you to do from the stations. I want new faces, new people.